brings us to dark matter, which is the hypothesized particle that constitutes the mass which is predicted by several different measurements showing a mass larger than what is seen from luminous matter. And we're going to collect here the different support for this dark matter model from observations that we've already talked about, including the rotation curves from spiral galaxies, which we looked at in chapter 8, where at large radial distances beyond where most of the visible stars are, you still, based on the rotation speed, suggest a large mass out in those very dark regions. We also just saw here in this chapter that using the random motions of galaxies within clusters, that you should get a larger mass than you can add up from the visible matter in the gas and in the stars of the galaxies. You have a third line of reasoning that we just talked about, which is gravitational lensing. So this is not based on the motion of galaxies, but is just based on the curvature of space-time around the galaxy cluster. So that's another method that gives you a mass which is larger than you get from the visible material. Related to those two lines of evidence is a very strong case shown in the image on the bottom left, which is the bullet cluster. So here we have two clusters of galaxies that we believe are passing through each other. So what you have in the middle is the intracluster medium that has now collided, and you see even a type of bow shock, a result of this collision, and it's shown by the red image of the X-ray gas. You can also then, in the optical image, see the individual galaxies, and what's shown in blue is where we believe the majority of the mass is located based on gravitational lensing. So again, the lensing is just the curvature of space-time, and the interesting thing with this colliding galaxy clusters is that we see the gas left in the middle from being smashed together in the collision, and that this idea of a dark matter particle, which provides the mass in the blue, can much more easily pass through each other if it's not directly colliding, if it has a much lower probability of collisions. So this is the bullet cluster. And then our fifth line of reasoning we'll hopefully have time to talk about in the next chapter, which comes from the early universe, where we have a remnant of the first light, which is the cosmic microwave background, and this then gives seeds for the formation of galaxies and clusters of galaxies. And based on these measurements, models predict that there should be dark matter. All right, so those are the lines of evidence for why a type of dark matter is necessary. You will then ask, what is dark matter? And the easier question to ask is, what is it not? Because it is not some of the obvious candidates. So we would think that this could be either very faint or invisible forms of normal baryonic matter. So baryonic just means the typical matter of protons, electrons, and what we think of as typical matter. And so you could think about a black hole is invisible, but based on observational limits, it seems like black holes cannot constitute all of the dark matter. In fact, they would be a very small amount. You could also think about very faint stars, such as brown dwarfs, but again, observations seem to show that they would only contribute a very small amount of the mass. Another option is antimatter, but then antimatter annihilates with regular matter and it gives off gamma rays in this annihilation, and you should be able to see those, and we don't see enough produced to explain antimatter being dark matter. You could think about neutrinos, which we know already and we've detected, and they are very fast moving, nearly the speed of light, relativistic particles. But the problem with any particles traveling that fast is that they then don't clump together into the distributions of dark matter that we see where you have a higher density in galaxies. They would basically just fly through. And then finally, related to the above points is regular matter that's charged, because if it were particles flying around and there's a charge, then it would interact with other charged particles, and again you would see the heat and collisions caused by these charged particles. So these are all evidence that dark matter should not be any of the above, but instead should be a low speed, or otherwise known as cold, and also very weakly interacting, not very many collisions. So this finally leaves us with not much that we can think about as good candidates for dark matter, even though there's a wide range, because we don't know what it is. You still are constrained in what the properties of that dark matter should be. And so two of the favorite candidates are either WIMPs, which stands for weakly interacting massive particle, which is not a particle that we've detected so far, so there's no direct detection of a WIMP. There are searches, and shown on the upper right is LUX, which is the Large Underground Xenon experiment that operated with a large amount of xenon, and it was underground, so it's a good description of the experiment. And the idea is that then dark matter would collide with the xenon, but so far none has been detected, and it's starting to put pretty strong constraints on if there are WIMPs, then they have to have a very, very small probability of ever colliding with regular matter. Another option besides WIMPs are axion-like particles, and these are also not standard particles and are not so far detected. Again, there are attempts to detect axion-like particles, including the experiment shown on the bottom left, which is CAST, the CERN Axion Solar Telescope. And this is quite cool. It's a very powerful magnet that the idea is if an axion or an axion-like particle passes through it from the sun, so this you can see that it moves on a track, and this is pointed at the sun, then these axions coming from the sun would then, in the strong magnetic field, would produce a photon that you could measure. However, again, there's no evidence that this is happening. So these searches will continue, and possibly in our lifetime we'll know if dark matter is real and if